We'll begin in a minute. Does anyone have any astronomical questions or course-related questions?
I'm still not understanding the aberration of starlight.
And you watched the video?
Yes, and I tried looking it up on Google and watching other videos, and it didn't help.
Yeah, it's a tricky concept.
Like, I understand the physics behind it, but I'm trying to, imagine, I'm trying to put it to mind with the Earth going around the sun and not just, the sun looking like it's moving.
Right, let me put up a few. So it's kind of the same concept as when you're sitting. I mean, I went through these slides in the video, so I don't know if this explanation will just be repetitious and equally unhelpful, but maybe me explaining it live will help. Now, if you're sitting in the train and it's raining straight down and the train's not moving, you just see the raindrops falling down. But if it's moving, you see the raindrops coming from your direction of motion. Like in this picture over here, the train right here, the train would be moving to the left, so you see the raindrops falling from that direction.
I mean, I understand that. It was like with this picture on the far left, I'm trying to think of how the Earth, in its orbital motion with the starlight.
Yeah, so let's see here. The star is way off in the distance. Earth is moving, in this case, to the left. And so you can rethink about this from our point of view. We don't feel our motion unless you're going through some kind of extreme acceleration. You don't feel it. So from our point of view, we're stationary and the star is moving. And you can flip between those two views. It's Einstein's principle of relativity. You can always say you're stationary and other things are moving. So from our point of view, we're stationary and the star is moving. And the star is raining light down upon us. But since just like those raindrops, they take time to travel, the light takes time to travel. If the light was instantaneous, we would see the star right there. But instead it's moving, and so the light we see is from when the star was back over here from our point of view. And so it is finally reaching us when the star is actually over there. And so from our point of view, we don't see the star where it is, but we see it a certain angle forward, because in reality, we're traveling in this direction. I don't know if that helped any better.
Yeah, that helps. How do you get the 20 arc seconds, though? What are the calculations?
So it depends just on the, it does not depend upon the distance. It's just about our speed compared to the speed at which these raindrops are falling, which is the speed of light. So our speed going around the sun is about 30 kilometers per second. And I've actually never done the calculation. Maybe try it here and we'll see what happens. 30 kilometers per second. The speed of light is 3 times e to the 5 kilometers per second. So that would be the angle in radians. And so if we divide by 2, divide by pi, times 360, that's in degrees, times 60, that would be arc minutes, times 60. Haha, how about that? Never did before, nailed it. So 20 arc seconds. And it's, even though that's big, remember, if you watch the video, stellar parallax, which we'll review today, is small. It's usually an arc second or less. Stellar parallax is easier to see because it's one star moving with respect to the stars around it. In this case, every star from that direction of the sky has that same shift. And so if you want to measure that 20 arc second shift, you have to measure it compared to the stars way over there, like in your direction of motion. So measuring 20 arc seconds over a 90-degree range requires precision instruments that work on a large swath of the sky. And so it took longer to measure this. And we won't be coming back to this concept. And if you did have trouble understanding it, it's not that bad. The other one, parallax, you really will want to be able to wrap your mind around. But the point is, you only get this effect if we're moving. And And, we didn't see it for the longest time. We eventually saw it. So for the longest time, we were consistent with the geocentric model, both with this and with stellar parallax. It's like, well, we don't see either of them. And the reason we didn't is our telescopes were insensitive enough. The stars are actually much, much farther away than we ever imagined. Our kind of guess was based on the Ptolemaic close packing model. Everything was packed in really close, so we thought the universe was quite small. And the fixed stars we thought were just right beyond Saturn. And we should have easily seen parallax if they're that close. For us to go centuries and centuries until telescopes got good enough, then we saw it, and that was the final death knell for the geocentric model. Any other questions? Okay.
Yeah, I don't know if you'll have time to cover this, but if you don't, it's okay. But I know for, as you mentioned, like with stars, it's 20 arc seconds, really regardless of distance. But how would that work with both planets and moons and stuff like that are actively orbiting? Would it just change the arc seconds that it's ahead, or how would that work?
Let's see. Yeah, it should work. I never really thought about this, but yeah, it should be the same for planets, moons, anything. It's not just stars. It doesn't matter about the distance. It's our relative speed. And so you have to take into account not only our speed, but the planet or moon speed and the speed of light. And they should also be shifted by this amount as well, not just the stars. And of course, the thing about it is, it does depend on our direction of motion, which is always changing. As we go around the sun, this 20 arc minute shift, that's on the sides of us. If we're traveling this way, it's all the stars here that have that forward shift by 20 arc seconds. And the closer we get to the direction of motion, there's no shift. And directly behind us, there's no shift. But as we go around the sun, we change our direction. So now it's these stars that have the 20 arc second, and this star has none. And then my chair doesn't rotate around all the other way, but you get the idea. As we go around the sun, it's different stars that are doing this. And you could invent a geocentric model where the stars are attached to the stellar celestial sphere with little epicycles that do these weird things, but it's really contrived. Now, the heliocentric model here is making and this will lead us into our first question, is making a very specific, very precise, very obscure prediction. And so if it's shown to be true, you gain a lot of credibility in that model. And it was shown to be true.
Okay, thank
you. Okay, so, good questions, good discussion. But let's jump into the warm-up question here. So this is about the scientific method, two-parter. Scientific method can be applied to ideas that make assertions, predictions, or testable predictions, one of those three. And the second part is the scientific method can be used to determine if such an idea is true, false, or either. Okay, and then you take those two and combine them together. So your answer would be between 1, 1 and 3, 3. Give you just a second for those who signed on at the last minute. See how many of you we have. Lots of you today, over 150 of you. Let's at least get it up to 100. Every time I set a goal, the counter stops right short of it. 99, we'll go with that. There we go. Okay, values. Show histogram. Okay, between 3.2 and 3.3. So I'm going to send you into the break rooms. What you all agreed on, it's testable predictions. So correct, testable predictions. So if someone makes a testable prediction, can we show it to be true, false, or either? Okay. And let's see, I got to remember how to do the break rooms. They're right up here. Breakout rooms. I'll put 3 of you in a room. Okay, great. demonstrating rooms. Rooms are open. Feel free to take a picture before you go, or if you just remember true, false, or either.
Dr. Reichardt, just to let you know, I think you put us into 3
Yeah, I
breakout
know.
rooms.
I sent a message into the breakout rooms. Yeah, I effed it up. Instead of 4 per room, I created 4 rooms. So they're like 50 of you in each room.
All good. It was a good party.
Yeah, good.
Yeah, we actually were able to still have a good discussion. So
Good. Yeah, I hope you just shout it out on top of each other, and we'll see how you do. They'll all close down in 5 more seconds. Everyone will be back. So go ahead and reinsert your answers. Normally I give a clue, but I wasn't sure what clue to give without giving it away. So we'll just see if you're able to figure it out. So you're now submitting either 3-2 or 3-3. Much better. Okay, 3-2 is what you went for. Yeah, so if a testable prediction, you go and perform the test, and if the test fails to meet the prediction, the idea is false. That's what the scientific method can do. It can rule out bad ideas. If it passes the test, it doesn't mean it's true. There could always be some other explanation that gives the same result. It just, the scientific path to truth is a random walk, and the scientific method prevents you from going too far in the wrong direction. It's like the childhood game, you're getting hotter, you're getting colder. It just tells you if you're getting colder. But it seems to have worked for us. We've built civilization with it. Okay, that's one. And let's do one more warm-up question. I'll reset the board here. How many disproofs of the standard geocentric model, oops, sorry, it's covered up. How many disproofs of the standard geocentric model have we discussed so far? So we've discussed a number in class. You had some video homework to watch, and yeah, count them up and see how many you come up with. I'm not going to send you in the breakout rooms. I just want to see how many you can think of typically. Give you another 10 or 15 seconds. Fewer responses. Let's see if we, well, okay, we just broke 30. See if we can break 35, and then we'll take a look. Almost, there we go. Okay. And let's take a look at this histogram. We'll go logarithmic, add a few bins. 2, 3, 4, 5, 6, 7. Okay, so we have a distribution here, and it's kind of peaking around 4 or 5 or so. I came up with 5. Maybe you've picked up some additional ones, but here's a good summary of some of the stuff that we've talked about. So in chronological order, we have the moons of Jupiter. So this is evidence of something going around not the Earth, problem for the geocentric model. Phases of Venus, which is good because it makes very specific predictions for both the geocentric and heliocentric models, and the heliocentric model passes that test. You may have also included the lunar features and the sunspots. I didn't include them on my list because they're not really testing geocentric versus heliocentric, though they are kind of wrapped up in the dogma of the geocentric model that was adopted by the church. That might explain some of the higher numbers. I didn't put them on my list, but I can see you including them. Then in 1729, the telescopes got good enough that we could do aberration of starlight as Earth orbits, and I assigned a video on that, and if there are any questions, I'm happy to answer it. But it's basically because light travels at a finite speed. If it traveled infinitely quick, we'd see the stars where they are now. Instead, we see the stars where they were when they emitted the light, and you combine that with the speed of our motion, and it makes it look like all the stars are coming slightly forward from a forward direction, from the direction of our field of motion just a little bit. Then stellar parallax in 1838, which definitively showed that Earth orbited the sun. We'll talk more about parallax in today's lecture, and the next lecture. It's a concept we'll keep coming back to. But basically with parallax, if we're viewing a nearby object from a different position, it appears to shift. So if Earth is orbiting the sun, all nearby objects will appear to shift back and forth. And the stars, they're very far away, much farther away than anyone ever had suspected. So it took a long time for the telescopes to get good enough to see that shift, but eventually by the mid-1800s we did. And then this one is a little bit more subtle, the Foucault pendulum. Again, this giant pendulum that we see within museums, but that is evidence of Earth spinning on its axis, which is a contradiction to the geocentric model as well. Okay, any questions about those? All right. So we're well behind, but maybe the dot cam won't break and we'll have more time than usual to compensate. So let's see. We've talked about the geocentric model. We've talked about the heliocentric model. With the geocentric model, we introduced, the models of Aristotle and Ptolemy, and Ptolemy's model is quite good, but it's not perfect. With the heliocentric model, we introduced Aristarchus, and then Copernicus, and Copernicus's modified model, and Galileo. Galileo didn't actually present a model; he just was able to come up with tests and lines of evidence that the geocentric model is wrong, and the heliocentric model is favored, but didn't actually predict where the planets would be in the sky. So the best we have right now is Copernicus's modified heliocentric model, where he had to throw in those epicycles and shifted orbits. And it's a little bit better than Ptolemy's, but it's not perfect. So there's clearly more to this story. So let's go back to the story of planetary motion. Hopefully this class will be half story time, and then we'll get into some math that will help you do some of the homework questions. So this next bit's kind of a fun story. It's a story of two people, Tycho Brahe, and Johannes Kepler. Opposites in many ways. One is an observer, one is a theorist, one is the mentor, one is a student, one is a geocentrist of sorts, one is a Copernican with ideas of his own. They didn't necessarily get along very well, and quite possibly, as we'll learn, they got along really poorly, depending on how you want to interpret some recent evidence about the demise of one, possibly at the hands of the other. But let's take the story a little bit slowly. Let's start with Tycho. So Tycho Brahe, or Brahe, I pronounce Brahe. He's 1546 to 1601. So he dies before 1609. That's when Galileo started using the telescope. But he's the observer, he's the mentor, and he's the geocentrist. And he's actually the greatest pre-telescope observer. And that may seem like a weird phrase. How can you be an observer, an astronomical observer, without a telescope? And so the way he would do it is, what he's doing is something called astrometry. Astrometry. It sounds a lot like astronomy, but it's a technical term. He's measuring the positions of things in the sky to the best of his ability without a telescope. And let me show you how he did it. So here we have here we have Tycho. And you look at the guy's nose and you may say, what's up with that? Come back to that in a second. Here's one of his observatories. I think this is his primary one later in life. He's an aristocrat, but he's not like a noble. So he still had to work for nobility, and they funded the observatory. And he would measure the positions of things in the sky very, very accurately. So this is how it works. This little window, as you have here's Tycho majestically pointing while other people are doing the hard work. But here's one of his assistants looking through a bore sight, and they can slide it up and down this semicircle with graduated measurements on it, and they line up objects through this window. This window is pointed on the meridian, the line that divides the eastern sky from the western sky. So you wait until the object's as high in the sky as it gets, and then you can shift up and down until you get it right in the middle of that little opening, and then you have a measurement of where it is when it crosses the meridian. And he was the best at this. He could measure these accurately. Maybe I'll slide this over to 1 arc minute, which is 1/60th of a degree. Now, if you're in the lab course taking pictures, you can measure the positions of those stars to a fraction of an arc second, which is a 60th of an arc minute. But without a telescope, just using the eye, this is about as good as you can do. The eye, as we'll learn, is like a telescope, and it has a blurring limit. Being a very small telescope, it blurs things out to about an arc minute scale. Anyway, he was the best at it. Maybe a few Tycho stories before we get into his science. So what's up with the nose? Oh, go ahead.
I was going to say, wasn't he famous for having a huge ego? So did he just get into like a fight with somebody over some arrogant comment and then get his nose punched out?
That's it, yeah. A lot of these figures that we're looking at have huge egos, and it's causing them problems in their lives. This happened when he was a student, like your age. You know, he's at school, like the equivalent of college or university, I believe it was. And I always thought, you know, maybe it'd be a good story. He's coming to the, defending the honor of some fair maiden or something like that. But no, some other student claimed to be a better mathematician. So it was a nerd fight, basically. And I don't know if he won or lost the fight, but he did lose his nose in the fight. But, you know, he's from a family of some means, so they got him a gold nose. I don't know if it's solid gold or it's just gold plated, but he walked around the rest of his life with a big gold metal nose, which is kind of cool. So that explains that. But yeah, ego. And then the other story, I'll tell the first half of it. It's the other end of his life when he died, because the story of his death is misrepresented in most textbooks. So he was having dinner with the king. A bunch of people were invited over for like a little mini banquet, and it was going on for a long time. They were feasting and drinking and drinking and drinking. And Tycho had to use the facilities. You know, he had drank too much. He needed to use the bathroom. But back then, you know, you don't just get up. The king's there. You sit until the king's ready to get up. He kept drinking and drinking, and eventually his bladder exploded. That's the story that has made it through the ages. And it's not true. If you drink too much, your bladder doesn't explode. You just pee yourself. And you know, he had some other problem with his bladder that manifested at that time. But again, huge ego, people didn't like him, so that's the story they told after he died, and it kind of made it through the ages. Now, the question is, what really happened to him? And a number of years ago, about a decade ago, they dug him up, his corpse, and extracted a fingernail or two. It's pretty gross. But fingernails are kind of like tree cores. The deeper in you go, you're sampling material that was laid down earlier, and the farther out is later. So it's a history, or like an ice core. And they studied it, and it's a little controversial. One team found at a particular layer in the fingernail a tremendous amount of mercury. Another team later went and checked, and they disagree with the first team. So take it with a grain of salt. But according to this first team, he was poisoned. And that is consistent with the problems that he had on that day. He didn't die right there, got infected, and he died days later. So it's quite possible he was poisoned. And so historians have gone through his life and tried to figure out who would do this to him. And they have some suspects, one within his family and one within his employ. I like the second one because it ties into our narrative today. But I'll save that. I'll come back to that. Okay, set that up. But before we get to that fun, let's talk about what he actually did. It's to warrant our time. We're not spending time here just to tell the goofy stories about his nose and his death. He did some really important things, and things that were actually in contradiction to his belief system. So you got to give him a little bit of credit. 3 things in particular. The first 2 have to do with parallax. And the first one is the supernova of 1572. I think I have a engraving here. Yeah, so here's an engraving of him majestically looking at Tycho's supernova, or so it's been called. A supernova, you probably know, it's a type of exploding star. The star is more than 8 times the mass of our sun. It will blow up at the end of its life, leaving behind either a neutron star or black hole. Our sun's not massive enough to supernova. Instead, our outer layers will gently lift off, forming this pretty thing called a planetary nebula that will kill us all the same. But, you know, massive stars are rare. They go supernova. But for one to go off in our galaxy, a galaxy of our size, it's only once every 100 years or so. It's a pretty rare event. We haven't had a good one for like 300 and some years, so we're overdue.
I have a question about our
Yeah, go ahead.
sun. Another professor told us that it was going to go into a white dwarf and not just a planetary nebula.
That's right. So
That part
the
of
outer
it?
layers lift off, forming a planetary nebula. The core remains behind, and that is a white dwarf.
Oh, okay. Thank you.
Yep. And we talk, so this is, we won't get this far out in 101, but if you come back for 102, we talk about white dwarfs and neutron stars and black holes and stellar
I
evolution.
plan on it.
Good. Okay, so yeah, and when these do go off in our galaxy, again, once every 100 years or so, they're really bright. Sometimes bright enough that you can see them during the daytime sky for weeks. They're pretty spectacular. I'm hoping we see one in our lifetime. You know, once every 100 years. Pretty good odds we'll see one in our lifetime, but we're overdue. Anyway, it's named after him because he was the one who studied it best. Everybody saw it. And the belief at the time was that this was an atmospheric phenomenon. And the reason that was the belief is they believed, well, first of all, the Earth's atmosphere went all the way up to the moon, which I think I mentioned previously. We now know that's not the case. The atmosphere is very, very thin, hugs the Earth. That's why climate change, global warming is a thing. There's not much atmosphere, so once humanity spreads across the whole globe, you can actually impact it. And in reality, then it's just empty space up to the moon. Back then, they thought it was all atmosphere. And beyond that, you had the planets and the stars, and that stuff was perfect. And if God made it perfect, why would it change? He would have made it perfect from the get-go, and it would have stayed that way. So anything that changed in the sky, they attributed to an atmospheric phenomena, which means they thought this supernova was between Earth and the moon. Now you can test this with parallax. So this is, if you watch the video, you learned about stellar parallax. I'll come back to that in a second. But this is Earth-based. There are two types of parallax. Parallax when you're looking at something from opposite sides of Earth, and parallax where you're looking at something from opposite sides of Earth's orbit. For nearby things, opposite sides of Earth is sufficient. For far away things, you need to do the full orbit to make a measurement. So this is presumably nearby. They think it's between us and the moon. So the idea is you would observe it, if you could, simultaneously from opposite sides of Earth. Let's say this is the moon, or maybe this is the supernova between Earth and moon as it was thought. And take the moon, for example. This is one of the hallmark problems. If you look at the moon from opposite sides of the Earth, it will appear to have a different position. Like if you look at it from this side, you'll see it over amongst these stars. If you look at it from this side, you'll see it over amongst these stars. It will shift. How much it shifts, I'm not going to say, because that's the homework question. But anything closer would shift even more. I will say the moon shifts more than a moon. I'll give you that much. From viewing it on one side of the Earth to viewing it on the other. So this should shift many moons. That should be easy to see. The moon's half a degree. Many moons is many degrees. And Tycho can measure accurately to an arc minute, a 60th of a degree. So he figured he'd nail the parallax. It's a little tricky because he didn't have observatories on opposite sides of the planet. He had just one, so he had to take a measurement, then wait 12 hours till he rotated around. And even in the geocentric model where Earth doesn't rotate, everything else does the same amount. So the math works out the same. And he measured and saw nothing when it should have been a slam dunk easy measurement. And what that showed is that the supernova is well beyond the moon, actually out there beyond many of the planets, out in the part of the universe that is supposedly perfect and never changing. And I won't go through this because we've spent a lot of time talking about other things. This was all in the video, what parallax is and how you can measure distances. If you didn't watch it, go back and watch it because that would be key, particularly in the next lecture that we have. There's stellar parallax, and yeah, okay. So his next object that he did this for was a comet was super bright, big comet 5 years later in 1577. Again, comets were thought to be atmospheric. He did the same test, and no, it's well out there with the planets at least. Okay, and then the third thing he did, and this is really the most important thing that he did, was his planetary data. For decades and decades, he measured the position of the planets. Every time they crossed the meridian, he got an accurate measurement. It's the best data set out there. So if you're trying to create new and better models for planetary motion, he's the guy you got to talk to. He has the data. If you have an idea, you test it against his data. Okay. So this brings us to Kepler. Go to a fresh sheet, Johannes Kepler. And his dates, again, I'm not going to test you on these, but I want you to know the relative order. Let's see, 1571 to 1630. So he outlived his mentor, which is actually part of the story. And he was the exact opposite. He worked for him. He was under the employ. He was a theorist. So he had different, he wanted to figure out planetary motion, not just measure it. He was a Copernican. He believed the sun was at the center. And so he knew the value of Tycho's data and went to him many times saying, hey, can I take a look at this data? I have some ideas I want to test. And Tycho's looking at this theorist saying, well, I've sat out every night for the past few decades collecting this data. And here's this young whippersnapper coming in and just wants to use it to prove or further examine a model that I'm against on religious grounds. Tycho put Earth at the center on religious grounds, although he had his own kind of different hybrid model that I think I'll show you in a slide or two. And, and Tycho clearly already thinks he's a great mathematician, so he's not going to think Kepler's more skilled than he is and can do better. So he kept saying, no, you can't have the data. Go work on these other tasks. And this really frustrated Kepler. There's Tycho again. And just a little aside, here's his model. He had a hybrid geocentric model. He had Earth at the center for religious reasons, the moon going around it, the sun going around it. But then he had the planets, and here's his comet that he studied. And I don't know if that's the supernova that there or not, but the planets anyway are orbiting the sun, which orbits the Earth. So it's kind of a hybrid, but Earth's still at the center of all things. And this was his favorite model, and he didn't care for Kepler trying to best him. And then he died under these strange circumstances. And the very same day, his family went to collect the planetary data because they knew this was his key life work. It was of great scientific value, and so they wanted to secure it. And it was all gone. And guess who had it? Kepler. That makes him kind of suspicious into the potential poisoning of his mentor. And they took him to court and said, the court said, you got to give all that back. And he gave it all back except the Mars data. He defied the court order, kept the Mars data. And because of that, we have Kepler's 3 laws, because Kepler was actually right. He did have a better idea, and he was able to explain planetary motion perfectly for the first time in history. Better than Ptolemy, better than Copernicus's modified model. He nailed it, got it right. So let's check in the time. We go until 2:10, so we have like 20 minutes. I think we might be able to get through Kepler's 3 laws, so let's give it a go. So the brilliant thing that Kepler did is he abandoned these 2 ideas, circular motion and uniform motion, or together uniform circular motion. It's been holding us back ever since Aristotle and Plato before him. And we've just latched onto these ideas. We insisted that the models be made up of circles and uniformly moving circles. And we got as close as we could in the geocentric framework, as close as we could in the heliocentric framework. But Kepler's going to abandon those. In the first law, he abandons circular motion. So it reads the orbits of the planets. Actually, in the video, all of our faces end up right here. So let me expand it so that's not blocked. Like in the recording, our faces and everything block the right-hand side of the screen. So Kepler's first law, the orbital paths of the planets are elliptical, not circular, with the sun at one focus. So we have to define a few terms. First, what is an ellipse? How do you draw an ellipse? So you could do this at home, make your very own ellipse, just get a string, tack it down with some slack, pull it taut, and then keep it taut and move the pencil or pen around. The shape that you'll get is technically an ellipse. The distance between one of these points, focus, it's called the focus, to the edge, to the other focus, when held tight, is constant, and that's what defines an ellipse. So he's saying the planets actually move on elliptical paths with the sun at one of these two positions. So let's just write down the terms because we're going to use them a lot. So you have an ellipse, you have this axis, this is called the major axis. This little one here is called the minor axis. And we don't use, although these are mathematical terms, we don't really use these in astronomy. We use two other terms. We use semi-major axis. That is half the major axis. So that's the semi-major axis, and we call that A, lowercase a. And so sometimes it can mean acceleration, but in this case it means axis, semi-major axis. And then the other term is the eccentricity. I won't give you the equation for it, but it's a combination of the major axis and the minor axis. So to understand the semi-major axis, what if we took these two focal points and brought them closer and closer together until they're on top of each other? In that case, what shape do we have?
Circle.
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 Yeah, that's right. So a circle is a special case of an ellipse where the two focal points are foci. Let me write that down as well. Focus is singular, foci is plural. If they're on top of each other, we have a circle. In that case, the semi-major axis is just the, what do we call it with the circle?
Radius.
Radius, that's right. In that case, the semi-major axis, the semi-minor axis, they're the same. We call it the radius. So if you want to think about the semi-major axis, think of it as the long radius of an ellipse, the radius on the long dimension of the ellipse. I'll show you a few different eccentricities. So eccentricity 0 is when the major axis equals the minor axis. And then, as we start to separate the foci and these two axes have different lengths, there's eccentricity 0.5, eccentricity of 90%, 99%. Most planets are on orbits that are almost perfectly circular, like Earth, for example. It's not exactly circular. It is slightly eccentric, I think less than 1%, less than 0.01 or something of that order. Now, some planets are more. Mercury is more. Dwarf planet Pluto is more. I think those are around 10-ish%. And some things are very eccentric, like comets. They go way, way out and they swoop in. Remember, the sun is just at one of these points. The other point is empty. So that's what he's saying in his first law. And I think I can explain how he came to that, how he was able to break the shackles of 13-some centuries of history, abandon circular motion. And it's because he was a Copernican. This is just my own personal private theory. I'll draw it out, see if you like it. I'll make this big so you can see it. And let me get the focus because I feel like I'm a little out of focus. There we go. So he studied the Copernican model, his modified model. So Copernicus was using circles. So here we have a circle. Here's the center of the circle. And to make the Copernican model good, he had to shift the orbits. So the sun is not here, the sun is over here somewhere. And he had to add little epicycles. So I'm going to draw those epicycles. And in Copernicus's model, the planet you know, it's orbiting counterclockwise, but the epicycle turns clockwise in Copernicus's model, 1 full rotation per orbit. So I'm going to draw it in. I'll start here, and I'll go 1/4, that's 1/8, 1/2, 3/8, no, 1/8, 1/4, 3/8, 1/2, 5/8, 3/4, 7/8, and back. Okay? Now if you connect the dots, what shape does that look like? An ellipse. And so probably, I don't know how Kepler came up with this, but he probably was drawing and said, hey, I know that shape, that's an ellipse. And he said, no, wait a minute, ellipse has 2 foci, and he calculated where they were, and they were there and there. He said, oh, the central body is at one of the 2 foci, because Copernicus had to offset it. So he said, now, that's not how you make an ellipse. That's not technically an ellipse. You can't make an ellipse out of 2 rotating circles, but that's probably as close to an ellipse as you can get. So Kepler said, maybe it just is an ellipse with the massive body at one of the 2 foci, and he checked it out, and indeed, that nails it. Okay, that's the first law. That's K1. I'll refer to that as K1. K2 has to do with, well, it abandons uniform motion. We just got rid of circular motion. Now let's get rid of uniform motion. And it's written in a really funny way. But basically, he's saying it moves around faster if the planet moves faster when it's close to the central body, the sun in this case, and slower when it's farther away. And then he tries to describe how much faster and how much slower. I'll come back to the words in a second. But nowadays we'd say, let's call this angle from the sun to over here 0. And we'd write down some equations. Says, okay, when the angle is 0, it's moving fast. 45 would be over here, a little bit slower. 90 degrees would be here, a little bit slower, and so forth and so on. 180 is over here, the slowest. And as you come back around, it speeds up again. We'd have some function for the speed as a function of your angle, at least the relative speed. And you can write that equation. It's really messy, really sloppy, hard to do, but you could do it. Kepler found a more compact geometrical way of describing it. That is correct. It's not how we would do it today, but it is correct. And it's really concise, which is kind of cool. He says, consider an imaginary line connecting the sun and the planet. This line sweeps out equal areas of the ellipse in equal intervals of time. So coming back here, when you're far from the sun, you're going slowly. So in the same amount of time, you sweep out a little bit here, and it's like a triangle, so the area of a triangle is 1/2 base times height. So small base because it's moving slowly, but a large height because it's far away. If you get close in, well, it's not shaped like a triangle anymore, but this distance, which was the base of the triangle over here, is much bigger, but the distance away is much smaller. So they kind of balance each other out. And if you work through the mathematics, and he proved it, and they balance each other out perfectly. The planet is sweeping out equal areas. So in this time when it's close to the sun, it's moving quickly, it sweeps out this light blue area C. And when you're far from the sun, it's moving slowly, it sweeps out this light blue area A. It's the same area. And here's the intermediate case B, it's the same area. So you can describe this motion very compactly by saying this imaginary line sweeps out equal areas in equal times. So obscure, old-fashioned way to say it, but it's right. Basically, the thing to remember is Kepler's law is describing relative motion. When is it faster? When is it slower? Now, it's not describing its absolute speed. How fast is it going on average, or at fastest, or at slowest? Or to put another way, how long does it take to go completely around? It's just relative. When is it going faster? When is it going smaller? To get the absolute speed, the time it takes to orbit, that's Kepler's third law. And we'll use this a lot. We'll do a lot of math with this, so I'm going to spend some time describing it. Kepler's third law states the square of a planet's orbital period, the time it takes to go around, P, is proportional to the cube of its semi-major axis which is the long radius of the ellipse, cubed. Let me write that down. So p squared is proportional to a cubed. Well, first, proportional. Let me explain what proportional means. Proportional means it's equal to some constant times. So we can rewrite this as p squared, the orbital period, is equal to some constant times the semi-major axis cubed. And Kepler checked this, every planet going around the sun, it's the same constant that relates the orbital period and its semi-major axis, how far away it is from the sun. Now, for the moons going around Jupiter, they also follow Kepler's third law, but with a different constant. And with our moon going around the Earth, there's only one, so we can't check it, but we can calculate the constant. It's a different constant. So this constant appears to change with the central body. Kepler had no idea why. Once we get to Newton in a lecture or so, we will know why. But right now, you just have to accept it. So let's talk about things going around the sun. That's the symbol for sun, a circle with the dot. Circle with the plus sign is the symbol for the Earth. Now, I'm going to teach you a new way to do math. That sounds really bold and ambitious. It's called the ratio approach. We use it a lot in astronomy. What you're used to is plug and chug. So suppose I gave you the semi-major axis in astronomical units, sun-Earth distances. Jupiter is 5.2 times farther from the sun than the Earth. So that's 5.2 AU. And I want to know how long it takes Jupiter to go around the sun in years. Well, you'd probably have to convert that AU to the MKS system, meters, because this constant's probably in MKS units. And it would come out in seconds, take a square root, and so you get the orbital period in seconds. Then you got to convert to years. So we have a unit conversion, a calculation with a constant, another unit conversion. Lots of opportunities for mistakes, but that's what you're used to, and plug and chug. The ratio approach gets rid of the constant and gets it to the point that you can almost look at the equation and give me an answer. So the ratio approach, you're always comparing some object to a comparison object. So this is the equation for the general case. Let me write that down. This is the general case for any object going around the sun. Well, let's introduce a comparison object. And a good comparison object's the Earth. That's an object that's important to us. So let's write the same equation out. This would be the comparison object for the Earth. The Earth goes around the sun. What's the orbital period? 1 year. So 1 year squared is going to be equal to that same constant. Anything going around the sun is that same constant. And our semi-major axis from the sun is, I just mentioned it, something we call the astronomical unit, 1 AU cubed. So 1 AU is the sun, Earth, semi-major, that's an A and a J, major axis. But since our orbit's almost perfectly circular, you can think of it as the sun-Earth distance. So for anything going around the sun, the top equation, for the Earth going around the sun, the bottom equation, let's just divide these two equations and simplify. So over here, we'll have period divided by 1 year, quantity squared. I kind of grouped those together. So period measured in years squared. The constant cancels. You don't even need to know its value. It's equal to, now group these, the semi-major axis measured in astronomical units cubed. This is much simpler. If I give you A in astronomical units and want P in years, no conversions, no constant. In fact, we often write it shorthand. P squared equals A cubed. Now, if you use the shorthand version, you have to remember to use consistent units. I'm going to write that out because that's important. Use consistent units. Exclamation. And consistent refers to the central body. When we're talking about things going around the sun, consistent units are years and AU. And we can check that. Now take the case of the Earth. It orbits the sun in 1 year, so 1 squared, is that equal to a cubed? Well, it orbits at a distance of 1 astronomical unit. 1 squared is equal to 1 cubed. Yes, it is. Just a quick check. Now, so anything going around the sun, if I give you AU or year, you use this equation, you're good to go. Now, some people have problems with fractional exponents. Again, we have a wide variety of math backgrounds and skills in this class. So let me pre-solve these for you in case you have problems with that. One way, you could take the square root of both sides. So P would be equal to A to the 3/2, pre-solved. The other is A is equal to P to the 2/3, pre-solved. So if you're taking an exam or homework and you're worried, you're not good with the fractional exponents, 2 pre-solved equations. So let's try it out. Let's try it out with Jupiter. I gave the example of Jupiter. For Jupiter, the semi-major axis is 5.2 AU. So A is 5.2. If I want to know the orbital period, it's this symbol. P is equal to 5.2 to the 3/2. Put that into a calculator, you get 11.9, and the unit is years, because that's the consistent unit. So I'll give you a number, you'll raise it to one of these fractional exponents, and then you have the other. You don't have to do unit conversions, you don't need to know the constant or anything. Flip it around, if I gave you 11.9 years, you raise it to the 2/3, and you come up with the distance from the sun in AU. Now let me just point out there's a common mistake. This will be the last thing we do today. A common mistake that people make, it's a calculator error. So the wrong way to do this would be 5.2 to the, that's your calculator symbol for exponentiation, to the 3/2. This is wrong because what the calculator will do is 5.2 to the 3. It'll do that first and then divide the whole thing by 2. What you want is 5.2 to the parenthesis, 3/2 unparenthesis. That will do this first and then raise 5.2 to that. Or you can just do that in your head, 5.2 to the 1.5. And so next class, we'll probably start with one of these calculations, and we'll also consider how this works out if the sun's not the central body, if the Earth or Jupiter or anything else is. You'll see it's the same process. Once you wrap your mind around this ratio approach, the calculations become really simple no matter what the central body is, and we'll work some examples using the SETI interface. Okay, and yes, 2:10 is when we stop, right? And so I'll stop now and stick around for questions.
Thank you.
Thank you, Dr. Reichert.
My
Thank
pleasure.
you.
Dr. Reichert.
Thank you.
Thank you.
Thank you.
I had a question about just a video. Did you email the one about the parallax? Did you email that to us, or is it on your YouTube page?
It's on the YouTube page. Go down to the bottom, you'll find COVID edition of 101 where I'm putting our videos, and under lesson 2, it's there.
Okay, thank you.
Dr. Reichert, I have a question.
Yeah.
In regards to the lab, I just started because I was kind of I don't know, just busy, and I just started my lab a day or 2 ago. Am I behind at all, or can I can get all my photos, right? Because I just got all of them.
Yep, you can get all your photos. So I went through and got rid of all the telescopes that are down because of COVID. So all the remaining telescopes are possible. You still have plenty of time. It's usually only a day or 2 to get observations back. You may just want to start by selecting the 2 prompt telescopes that remain. But as you get closer to the deadline, if you're getting desperate, just submit on all telescopes I've given you access to.
Okay, thank you. Also, Maki Maki it said it couldn't observe Maki Maki with the telescope, so.
I haven't checked them all, but each semester there will be different objects that are not observable because they're just too close to the sun.
Okay, got it. Thank you.
Sure.
The exams, how long will we have to take them once we open them and start them?
So I've set it up that you'll have 24 hours and you can come and go. You can start, you can stop. Normally that's not how we do things. Normally it's in class 50 minutes and the final is 3 hours. But I'm giving you 24 hours just because of the unusual circumstances this semester. And it will be open book, open notes, because I can't control that. Normally I let you bring a cheat sheet into the exam, 1 page front and back. And I'm still going to recommend that you make them because it is a great way to consolidate the knowledge and really understand what's going on. But yeah, that's going to be the format.
Okay.
And same with the final exam. I've gotten special permission that the final exam does not have to be on our scheduled day because section 1 and section 2 have different scheduled days. I'm going to move you all to the same day. You have 24 hours so we don't violate the rules of overlapping with other exams. And yeah, the final will work. It'll be longer, like 70 questions for the final, 25 questions for a midterm. And the final is cumulative with an emphasis on new material, but it'll work the same way. It'll be through WebAssign.
I have a question that doesn't necessarily pertain to this class, but it does to the astronomy community as a whole. Is there an area in the astronomy community where there's like almost beef in terms of like there's contention on a certain stance or something like that, and where astronomers often fight on it, or it creates like divides?
Yes, in every field. When you're working on the cutting edge, it's in every field. Now, people have this idea of we go to conferences and we politely take turns giving our presentations and everyone nods in agreement because we're all scientists and we somehow just magically know truth. But that's not how it works at all. I've explained how the scientific method works. It's this random walk where we don't know where to go and we just know when we've gone the wrong way. And so when you're working on the cutting edge, people are throwing out ideas and then the hands go up and everyone tries to take down every idea. Even if it's like your friend up there, it's nothing personal, it's just how science works. And because some people come up with hypotheses, those are the theorists. And then you have your experimentalists whose job is to disprove them because again, we can't prove things to be right, we can only prove things to be wrong. And so very contentious and money is on the line. Careers are on the line. If you're a theorist, you're actually, depending on the type of theory you do, you're only expected to be right maybe 1 every 5 or 10 times. You're an idea generator. Now, if you never come up with an idea that's shown to be correct, if they're all disproved, you're not going to get any more funding. And experimentalists, it's very competitive as well. You got to be really good at it and not make mistakes. So there are egos on the line, there's money on the line. We're working with the unknown with a method that doesn't point us in the right direction, just tells us when we're making a mistake. So yeah, it's messy, it's sloppy, and by the time we figure it out and present it to the public, it's been cleaned up and sterilized.
Is there a current stance that causes that there are different sides on that astronomy?
Oh yeah, all sorts of things. Maybe a good one is in the area of cosmology. We've been measuring Hubble's constant forever, getting better and better at it. And what that is a measurement of the expansion rate of the universe. But now that we've gotten really good at it, we're learning that different techniques are giving different results. And techniques that use things in the nearby universe give us an expansion rate that's faster than things from really far away in the universe. And so people are fighting like, well, your technique has flaws in it. And I mean, they've given out Nobel Prizes for these things. These have been very, very carefully checked. And so they're like, no, our technique's right. Your technique has a flaw. Or maybe we just don't understand the physics, and it's a big confusion. In the theory world, black holes, it's an absolute nightmare. The theory's producing all sorts of internal contradictions, and there's not much empirical evidence to help us decide between these things. And so some of these conferences, they maintain decorum, and sometimes there's shouting and screaming and dropping the F-bomb, and not quite blood on the floor, but
Hard.
yeah.
Is the rate of expansion constant, or does it like slow as it reaches farther from the
It is
epicenter?
changing with time too, and those are other issues, but people are disagreeing just on the current rate
Okay.
now based on different techniques. The local universe suggests that it's moving faster than expanding faster than the universe as a whole. Einstein's theory does not allow for that.
All right, thank you. I was just curious about the community.
Oh, sure. It's fun. It's lively. You just have to have a thick skin. And if you want to be successful from a grant point of view, you better not make too many mistakes.
Thank you.
I have a question.
Yeah.
For the you had said that for like the very bottom portion of the class that gets an F, you usually give them a D, right?
Yeah, as long as you've tried everything, I am sympathetic. If you
Okay.
got an F because you skipped a bunch of homeworks and you didn't do the extra credit to try to make up for your skipped homeworks, or you skipped an exam, because you are allowed to drop one homework, one exam, but if you just like skipped the first exam, didn't even give it a go, and I'm less sympathetic. And normally there are people who didn't do 4 of the 9 homeworks.
Okay.
Yeah.
For the people who decide that they need to do a pass fail for this class, and a D is a low pass. I don't know if you would know this, but does that low pass still count towards graduation?
So I just turn in the letter grade, and they convert that into pass or fail. I don't know if they have different gradations for low pass or high pass, and I'm not sure which letter grades map to what. Maybe D probably is pass. Do you know?
I think
do
it's
they
a
distinguish pass and low pass?
C- and a C- and a D or something along those lines is a low pass, and a C
And
and
above.
above is somewhere between a pass and a high pass.
So you'll
But
have
D
to
is
talk
still
to
a pass.
them. I don't know the answer. You'll have to talk to academic advising if a low pass will allow you to count this as successfully completing your science requirement.
Okay.
I would
Thank you.
think it does. Something like if you're doing a minor, there are often extra rules where you have to get a C or better. And so
Yeah, this is my graduating semester, and this is an elective class.
Mm-hmm.
So yeah, I'm not sure that there would be any specific requirements, especially because it really doesn't pertain to my major.
Yeah, but check.
Okay. Thank you.
Sure.
Dr. Reichert, when is the first test?
The first test, check my calendar, it's on my other screen. It's in the syllabus too, but the first test is currently scheduled for September 25th. Though we are running about a week behind on each homework. And so there's a chance that the exam will get delayed. I have to get through lesson 3 before I give the exam. I am catching up. It doesn't feel like it because of we're losing a day for Labor Day, but I should be done with lesson 2 in the first half of the lecture on Wednesday. So I'm 1 and a smidgen lectures away from finishing that. That gives us some time to do 3. Anyway, it's currently scheduled for the 25th, but there's a possibility I'd slide it. And since everyone's at home anyway, I don't feel too bad about moving an exam. Normally, I try to avoid that because people plan activities and events around it, but there are no activities or events anymore.
For those of us that have a lab on Monday, are we going to be expected to join another lab again? Because Monday is Labor Day and we don't have.
Oh, there are no labs on next week because of Labor Day.
Okay.
Yep, next week is blank. And so let me just check my calendar on that to be sure. But if there is an official holiday, we don't schedule any labs that week. That's correct. There are no labs next week. So that gives everyone, I didn't realize this, but it gives everyone yeah, but lab 1 is still due on Friday the 11th. Yeah. Okay, yeah.